So these are the solutions to workshop 1. For question 1, what I was looking for was to have you interpret the region whose area is found by the integral by just describing geometrically what this region looks like. I wasn't looking for you just to say just to basically translate the integral into words, but to understand that as we look at this subtraction problem in the integral, we're actually describing a region. So let me just draw for you what I had in mind. Oops, there we go. There's the pencil. Okay, so what I had in mind was really this: that if you look at these two expressions, what this is clearly a top minus bottom type of integral. What the region looks like is y equals x to the fourth plus 3 is really that curve, and let's put it in a different color. Y equals a square root of x plus 4 is going to be the square root function just shifted to the left like that. So this is y equals square root of x plus 4. This is y equals x to the fourth plus 3. And we're integrating on negative 1 to 2. So there's negative 1, and then we'll just go up to 2 like that. So we're looking really at that region in between those two curves. The thing to recognize is that there are actual boundaries. Just saying it's the integral of top minus bottom on the interval negative 1 to 2 is not really describing the boundaries. So that's why I wanted you to be very clear about the fact that the region is bounded on the top by y equals x to the fourth plus 3, on the bottom by square root of x plus 4, on the left by the line x equals negative 1, and on the right by x equals 2. The key here is that if I had somehow done this in the y direction and described the same region, you should get the same answer. In other words, this is a region independent of the fact that I've set up an integral to do it. You should be able to actually read the description of a region off of the integral. All right, so next question. So in this question, what I was looking for you to do was describe what the top and bottom functions are in this integral. So it's clear that if I graph the region, let's once again put in top and bottom. So what we have here is that this is top and this is bottom on the interval 0 to 2. So that's really going to be that region like that. And then once again we have top and bottom on, let's see if we can do like a slightly different one. There we go. So that's top and bottom on now the blue region going from 2 to 4. All right. So the idea is that this really gives the area of a region that's above one function and below another function if you understand the functions in the way that I'm thinking of. This region extends from x equals 0 up to x equals 4. You can clearly see is that this is the bottom function, and really it's this whole thing up here. It's this sort of whole top boundary that constitutes the top function. So we have to define that. And the way that I would do it is I would say that f of x is equal to x squared plus 3 for at least the interval 0 less than or equal to x less than 2, and it's equal to 9 minus x for 2 less than or equal to x less than or equal to 4. And by the way, you're wondering, why did I say less than 2 and then put another, why is this one going to be less than and this one is less than or greater than? The truth is it doesn't matter because you're going to get the same value. What would be incorrect, would be completely incorrect to do, would be to define it that way, because you can't really define, you'd be defining it in two different ways for the same point. It's like, yes, it comes out to the same value, but it's kind of considered sloppy to do that, because of course we know there are plenty of piecewise functions that where they don't meet up at their transition points and you wouldn't get the same value. So you want to make sure that that in a piecewise function, every x value is defined in only one way. So anyway, that's the definition of x, and then of course we can see that g of x is just equal to x minus 1. That's a constant. So this is real, and the interval, by the way, we asked on what interval the expression gives the area. The answer to that is 0, 4. So in fact, it's correct to say that the area is equal to the integral from 0 to 4 of f of x, of f of x minus g of x dx. That would be a completely correct expression for the integral once the integral is defined, once the f and g are defined in this way. Okay. Let's go to number 3. So we have here is we have an integral that gives the area of a region using a dy integral, and I've asked you to set it up as a dx integral. So the first thing I want to do is I have to graph these functions. We know that for a dy area integral, it's going to be right minus left. I still find it easier to graph lines when it's y as a function of x than x as a function of y. So I've actually converted them into y as a function of x just so I can see them. What you see is that x equals 6 minus 2y is equivalent to y equals 3 minus 1/2 x. In other words, I just solved for y in terms of x and then did the same for the green curve, the green line, x equals y minus 3. And I got what you can see is the green line on the left and the blue line on the right. So we know that what the region that's being described by this dy integral is, just put in 0 and 3, is just going to be the region that lies between this right line and the left line, going from a y value of 0 up to a y value of 3. Remember, this is a dy integral, so the limits of integration refer to the lowest and highest y values. So you can hopefully see why this yellow region is in fact the region being described by the integral. So now that I actually have the region, I can see how I would do this in the x direction. It's going to be broken up because the top boundary kind of changes at x equals 0. I'm going to have to do this as two separate integrals. So to write it that way, let's see, this is going to be, the area will be equal to the integral from, I see that the lowest x value that appears in this region is negative 3. And since I'm breaking it up at 0 because the top boundary changes, I'm going to do negative 3 to 0 of the green curve. Remember, since this is going to be a dx integral, I have to write everything in terms of x. I can't have any y's in a dx integral. So this is going to be x plus 3 dx, and then I'm going to add in the part that's to the right of the line x equals 0. That's going to be a low value of 0 going up to a high value of 6. I just solved for that point of intersection with the x-axis. It's going to be this line intersects the x-axis at x equals 6, so that's how I know I'm going up to 6 there. Or more to the point, the highest x value in this region is x equals 6. So that's just going to be 3 minus 1/2 x dx, and that's the answer. Okay, question 4. We're given an integral and we're asked to make an appropriate choice of u to complete the integral so that it looks like this. And of course I've kind of anchored you to what the choice of u has to be by saying that once I choose u, if I plug pi over 6 into that choice, I should get 1/2. Because we know that we have to change the limits of integration from values of x that you see here. These are x, and I have to change them so that they're values of u instead. Now, you might think that you could make any sort of choice. It's correct to say, for example, that if I chose u equals 3 over pi x, then it is correct to say that u of pi over 6 would be equal to 3 over pi times pi over 6 equals 1/2, and that would give me the 1/2 that I'm looking for in the bottom position. But let's be honest, that's not really what's suggested by the problem, and it's not going to work very well with the rest of the problem either. So let's try that again. What we can see instead is that the inner function here, if you focus on this, where there actually is a composite function, is sine of x. So the better choice is going to be u equals sine x. That gives us du equals cosine x dx. So now what we can see is that I can replace sine to the 1/4 x. Since u equals sine x, that's going to be u to the 1/4. F of sine x is f of u, and then this cosine x dx just becomes du. So I already have a du here. It's given to me in the problem. This is going to be u to the 1/4 times f of u, and then all I need to do is figure out what goes up here, we can confirm that that if I plug in pi over 6 into the sine function, I do in fact get this 1/2, so that's correct. And then at the top, we're just going to have sine of pi over 2, and that's 1. So that's the answer there. Now let's go to number 5. So again, we want to make an appropriate choice of u, and it's kind of suggested by the limits of integration that you see here. What I want to do is I want u of 4 to equal e to the 2, and I want u of 10 to equal e to the 5. Hopefully you can recognize that what I'm doing here is I'm dividing 4 and 10 by 1/2 and raising them to the power e. So the choice that sort of makes sense is going to be u equals e to the x over 2, because if I treat these as x values and I plug in 4, I'm going to get e to the 4 over 2, which is e squared, and that goes in the bottom position in the integral. And same with 10. E to the 10 over 2 is e to the 5th, and that goes into the top position. So let's see. In that case, du is going to equal 1/2 e to the x over 2 dx. So let's see what I have to replace here. I'm just going to rewrite this. So this is going to be integral from 4 to 10 of e to the x over 2 square root of 1 plus e to the x dx. All right. So the e to the x over 2 dx, I almost have that in du, except that I'm going to have to say 2 du equals e to the x over 2 dx. So this, even though they're not next to each other, they're going to be replaced with 2 du. And the other thing to recognize here is that e to the x over 2 squared is equal to e to the x. So that means that I can replace e to the x, this is going to be like u squared. In other words, since u equals e to the x over 2, that means that u squared equals e to the x. So this is going to be the square root of 1 plus, it's not o, of 1 plus u squared, like that. And so that gives us, let's see, and of course these are going to get replaced when we do it with u. It's going to be e squared and e to the 5th. So what I'm going to write in here is the square root of 1 plus u squared and then times 2, because it's actually 2 du that replaces the e to the x over 2 dx rather than just du itself. So that's the answer to 5. All right, let's go on from there. All right, so we have this 4-part function based on this setup where we know that f of x is even and g of x is odd, and we're given what integral from 0 to 2 of f of x and integral from 0 to 2 of gx are equal to. All right, so first of all, let's just make sure everybody's clear on what the important rule is for this. The rule is that the integral from negative a to a of an even function, I'm going to call it e of x, not the number e, just an even function, this is equal to 2 times the integral from 0 to a of, of e of x dx, and the integral from negative a to a of an odd function, I'll call it o of x dx, is just equal to 0. I covered in the video why that is. I'm not going to go over it again. You can review the video. So anyway, what we want to do is we want to use these rules to break up the integral that you see here into its even and odd components. So this is going to be written as the integral from negative 2 to 2 of f of x dx plus the integral from negative 2 to 2 of x squared dx, and then minus 4 times the integral from negative 2 to 2 of x to the 53 dx. Now the thing to recognize here, of course, is that we know that this is even because it's given to us that f is an even function. We know that this is even because we know that even powers of x are even functions, and for the same reason odd powers of x are odd functions. So that means that this integral here, from negative 2 to 2 of an odd function, is just going to equal 0. And these other two I can replace with their slightly simpler forms. This is going to be 2 times the integral from 0 to 2 of f of x dx plus 2 times the integral from 0 to 2 of x squared dx. So we know that this, we're given the fact that that's equal to 30. And so this is going to equal 2 times 30. And we'll have to actually evaluate this one the old-fashioned way. This is going to be 2 times the antiderivative of x squared is x cubed over 3 from 0 to 2. That's just going to be 8 over 3 minus 0 over 3. So this is going to be 60 plus 2 times 8 over 3. So that equals 180 over 3 plus 16 over 3 equals 196 over 3. Okay, that's part A. Now, part B. The thing to recognize here is that this is an odd function, but you're going to have to show that it's an odd function. Let me just show you what a number of you did, which was incorrect. A number of you wrote integral from negative 2 to 2, that this is equal to the integral from negative 2 to 2 of f of x dx times the integral from negative 2 to 2 of g of x dx. You should have received a little deduction for that because that is wrong. There is no rule that says that the integral of f of x g of x equals the integral of f of x dx times the integral of g of x dx. This is not a rule. It looks persuasive and it got you the right answer, but it got you the answer by completely the wrong method. And this class is really all about the methods. None of it is about the right answers, or very little of it is. It's really all about understanding the methods. So let's try again. What I want to do is I want to say h of x is equal to f of x g of x, because that's the function I want to integrate. And the question is h of x odd, even, or neither? Well, we can evaluate that simply by evaluating h of negative x and seeing if we get either h of x or negative h of x. So this is going to equal f of negative x, g of negative x, and that equals, we know that f of x is even, so that means that f of negative x has to equal f of x. That's what it means for f of x to be an even function. And we also know that g of x is odd, so that means that g of negative x equals negative g of x. Multiplying all that out, we get negative f of x g of x, which, given the way we've defined h, that equals negative h of x. So h of x is an odd function. That means that the integral from negative 2 to 2 of f of x g of x, it's an f, that equals the integral from negative 2 to 2 of what we now know to be the odd function h of x, which is 0. So this comes out to 0. If you tried to apply sort of this false rule, you would have gotten the right answer, because you would have just gotten 60 here and 0 here, which of course multiplies out to 0, but this is not the right reason for the right answer. So, okay, let's go on to the next ones. There we go. You really have to do the same thing here for C. We're going to do h of x equals x g of x squared. So this is going to be h of negative x equals negative x g of negative x squared. In other words, I'm just plugging in negative x every place I see x. So that's going to be negative x times, we know that g of negative x equals negative g of x, so that's like negative 1. Oops. Sorry, so that's like, sorry about that. So that's like negative 1 times g of x, and we're still squaring that. So that equals negative x times negative 1 squared is 1. G of x squared is just g of x squared. So that equals, let's see, we have negative x g of x squared. That's of course just the negative of this, so that equals negative h of x, and we can see that once again we're integrating an odd function, so the answer is 0. There we go. Okay, so, all right, so we can do this one now. This one has to be done by U-Substitution, or it doesn't have to be, but it's a little easier to see if it is. So let's use, we can see that there's clearly an inner function here, so let's try this. Let's let u equal x minus 1 and du equals dx. So that means that this integral is going to equal the integral of 2 f of u plus, if u equals x minus 1, then that means that x equals u plus 1, so that's going to be u plus 1. And then finally we'll replace the dx, and that gives us du. We change the limits of integration. We plug -1 into the expression for u, so that gives us -1 minus 1 is -2, 3 minus 1 is 2. And now we have that familiar -2 to 2 sort of an integral. The thing to recognize is that if we're given the fact that the integral from 0 to 2 of f of x dx equals 30, then it's also the case that the integral from 0 to 2 of f of u du is also equal to 30, because it doesn't matter what variable we use. So we're just going to break this up. This is going to become 2 integral from -2 to 2 of f of u du, and then plus the integral from -2 to 2 of u du, plus the integral from -2 to 2 of 1 du. U to the first, this is an odd function, so this whole thing just becomes 0. Next thing to recognize is that 1 itself, the constant 1, is an even function. How do I know that? Let's define h of x equal to 1. H of -x then equals 1, which equals h of x, proving that h is an even function. So a constant function is even. Now, what we have to do is we're going to use the rule that we know about f of x being an even function, knowing what its value is, to just convert this. So we know that the integral, this is going to equal 2 times, I'm going to replace that bracketed part with 2 integral from 0 to 2 of f of u du. And that becomes plus, this is now going to become, well, actually I don't need to do it that way. We can easily see that the integral of a constant function, this is the constant 1 on the interval -2 to 2. Its integral is just going to be the area under the constant function 1, which is just the area of this rectangle, which has a height of 1 and a width of 4, so that's just going to be 4. So this is now 2 times this integral here is 30, and then plus 4, and that comes out to 124. Okay. Finally, problem number 7. So we're asked for this integral, what function does that give the average value of on the interval -3 to 8? Well, you know that the average value of f of x on -3 to 8, on interval -3 to 8, is equal to 1 over 8 minus -3 integral from -3 to 8 of f of x dx, which, simplifying that a bit, that comes out to -3 to 8, 1 over 8 minus -3, that's 1 over 11, and I can just bring the constant in here. So that's the average value of f of x on the interval -3 to 8. So I'm told that that's also equal to the integral given in the problem, so that has to be equal to the integral from -3 to 8 of the square root of x squared plus 5 dx. What that means really is that these two expressions must be equal to each other. So we're simply going to set them equal to each other and solve. So that gives us 1 over 11 f of x equals square root of x squared plus 5, and I just solve for that and get f of x equals 11 square root of x squared plus 5. Now, the point that I'm trying to make here is this. Many of you are looking at this and you actually see this sign, you see the integral sign, and you just reflexively want to find an antiderivative. We will actually learn how to find the antiderivative of x squared plus 5 a little bit later in the course, but as of now I specifically gave you one that you wouldn't know how to find the antiderivative of unless you've looked a little bit ahead, to emphasize that finding the antiderivative is not always the right thing to do just because you see an integral sign in the problem. There are an awful lot of things you can do, and there are an awful lot of questions that we can answer about integrals other than just finding an antiderivative. So if you looked at this and said, well, there's an integral sign, I have to find the antiderivative in order to solve this problem, you're not thinking about it the right way. Hopefully if you can see the way that I set this up, and hopefully you realize that that's what I was asking you to do here. Okay.